should be able to.
Yeah, I would like to use this just to point.
Yeah, just as a pointer.
Yeah,
okay.
just as a point. Okay.
Fine.
Then I can move maybe with
You
the
can move
arrow.
it there.
Yeah, perfect. Okay. So thanks for the introduction, and thanks to the organizer for the organization of this nice event. I would like to speak about fractional boundary value problems. That is, in my opinion, this is like a toy model, and but maybe it could be interesting in the sense that may have we have here a look at the possible further extension, maybe in higher dimensions, for instance. And however, we have a neat equation. This is a fractional boundary value problems in the sense that we have a fractional boundary condition, and the fractionality is given by a non-local operator in time. So this this problem can be regarded as a kind of dynamic boundary condition. And the derivative with respect to time is given by, as you know, the Caputo-Zerbachian derivative. And as I said, this is a kind of toy model. And I have here some results just about the case in which alpha is between 0 and 1. And otherwise, I have no probabilistic representation. Of course, I am able to find the analytic solution, but I'm not able to find the probabilistic representation. So what actually the process, how the process is moving, and the behavior in the boundary, that is, in this case, is 0. Another problem is that I have results only in the case in which f is constant, that is equal to 1, which is the case in which we are studying the lifetime of the process. And otherwise, I have, until now, no probabilistic representation. So in order to have a clear picture, let me first say a few words about the fractional Cauchy problem, which is well known. There is an old story about this problem, and many researchers have to be mentioned here. For instance, let me recall Merchard, with evidently pushed forward the research on this topic, and Mainardi Caputo, of course, okay, because they introduced the fractional derivative I am speaking about. However, the fact is that I would like to underline here just the reading of this formula, the reading of this problem. That is, very often we can consider the microscopic point of view and the macroscopic point of view. That is, if I look from a distance, what I see is a particle, let's say, which is moving in a domain. Then this particle can stop for a while, and then the particle starts once again. So this is what I see if I look from a distance. Okay, so this kind of motion can be well represented by a time change. That is a Brownian motion, time changed with L, which is an inverse to a stable subordinator. So the new clock L gives, along the path of a Brownian motion B, the motion. That is, I already have the path, which is a Brownian motion. Then with the new clock, which is LT, then the particle moves along the path. Then, according with L, the particle, let's say, the particle decides to stop for a while, and then it moves once again. Okay. So this is as to say that the process may be delayed in some region of the domain, because if you have a bounded domain in that region in which the motion slow down, we have a delay, and this could be regarded as an approximation of the real situation that you can see in a microscopic point of view. That is, if you look closer, you can see that actually you have a Brownian motion, but this Brownian motion is moving with, let's say, its velocity in a non-homogeneous domain. So the fact is that we have to characterize we have a geometric characterization of the medium. Okay. So this obviously holds for general Markov processes. Then we have the same story. And another main part of this story is that since we are moving along the path of the Brownian motion, we already have a continuous process. So the behavior on the boundary is the same. That is the behavior on the boundary for the base process X, that for the time-changing process X is the same because L is continuous and the base process is continuous. Okay, so concerning the fractional boundary value problem, that is the problem I am interested in, a possible reading for this problem is that we have an evolution in the bulk. We have an equation in the bulk. In our case, we have the heat equation. And this evolution can be considered, can be given by a process, let's say X. That is, we have X on the bulk, which is a process with the proper evolution equation. So we have an evolution in the surface that is in the domain. Obviously, we are looking here at a domain which is not zero infinity. We have a higher dimension. And the evolution on the boundary is given by a fractional equation. So the process Y, which is the process driven by the fractional equation on the boundary, maintain the same property as I had discussed before in the previous slide. So this process Y can be delayed in some region of the domain, or can represent a good approximation for a motion given in an irregular domain with possible traps, if you like. Then we have the process zeta, which is the process driven by the fractional boundary value problem, and the process zeta on the boundary coincides with X. The process zeta on the the process zeta on the bulk coincides with X, and the process zeta on the boundary coincides with the process Y. So this is the main reading we may have when we are looking at this problem. Fractional dynamic boundary condition. So in order to have a picture of this fact, let us consider the sphere, for instance. So you have a three-dimensional motion inside the ball, according with an heat equation. When the process hits the boundary, can decide to reflect instantaneously, or the process can decide to move on the surface. If the surface is a non-homogeneous medium, for instance, then the motion is anomalous, according with the evolution on the boundary, which is given by the fractional equation. Okay, so I will like to go very fast on this slide, but just to recall a few facts. In particular, we may focus on formula number 5 and formula number 6. So the standard theory for a general macro process is that you have a macro process with a generator, then you can write the solution by considering a probabilistic representation of X tilde, and in terms of its lifetime. So you may consider, for instance, in a bounded domain, very often we consider Neumann boundary condition for X, that is, X is a reflected Brownian motion, which is killed or stopped at some time according with its lifetime. So this representation occurs with the representation given by a multiplicative functional, MT, and our case is given by the case in which we have F, which is 1. So we are looking exactly at the lifetime of the process. So we have some example, which this is very standard. So by characterizing the multiplicative function, the functional, we have the Dirichlet, Robin, or Neumann boundary condition. Okay, so we can start from the elastic Brownian motion. So we have a characterization given in terms of the multiplicative functional, which is given by here by an exponential with the local time of the reflecting Brownian motion X. This is quite standard. The local time is the local time at 0. And this is the generator, obviously, of the process, where C bar is the elastic coefficient. So the lifetime in this case is written in this way, according with an exponential random variable. So the process is stopped once the local time is greater or equal than this value, which is an exponential random variable. So the connection between the elastic Brownian motion and the fractional boundary value problem I have presented at the beginning is that I will show that as alpha goes to 1, the boundary condition you can see here gives the elastic condition you can see here. So we have connection in the sense that this condition for the elastic Brownian motion coincides in some sense with this condition as alpha goes to 1. So here you have a Caputo Zerbachian derivative of order 1/2, and C bar is a function of these parameters here, which is the inelastic coefficient. Another connection is given by the sticky Brownian motion. Actually, I don't have this connection directly because I can deal only with alpha between 0 and 1. Okay, but alpha equal to, this is possible. And in this case, this condition, the condition of the fractional boundary value problem as alpha goes to 2 becomes the ordinary derivative. And the ordinary derivative, since we are looking for solutions satisfying the heat equation, the derivative with respect to time is actually the second derivative of u. And then this condition becomes this condition here. And this problem is the problem associated with the sticky Brownian motion. It is a Brownian motion with the solution as this probabilistic representation. Then you have a reflecting Brownian motion, time changed by v, the inverse of v. And this is the multiplicative functional, time changed also in this case, and v is this time change here. So you have t plus the local time. Okay, so this is very interesting cases. These are very interesting cases. The case alpha equal to 1 and the case alpha equal to 2, in which we have two well-known processes. Here we have something understandable because the first derivative with respect to time gives obviously the second derivative with respect to space. So the sticky boundary condition appears naturally, let's say, in this case. But what is not so natural is the case in which alpha goes to 1, in which we have connection with the elastic Brownian motion. Of course, also in this case, we have a multiplicative functional, and then you can see the problem, as I said before, as an elastic condition. Indeed, this is the elastic sticky Brownian motion. So we have not only absorption, but we have also the elastic coefficient here. Okay, so just to introduce not some notation, not very, very quickly. This is the Caputo derivative with respect to time, obviously. This is the Riemann-Liouville derivative. We have this connection, which is well known, for function v, which are absolutely continuous. So this space here coincides with this space here of integrable function with first derivative, which is integrable. And since once we have v0 equals to 0, then these two derivatives coincide. So it is important to introduce also this space here, which is the space above extended with the function which are 0 at 0. This actually looks like a kind of zero exterior condition. And some further notation and definition. We have H, which is a stable subordinator, then is defined by this classical, is characterized by this mean value here. Alpha is in 0, 1. L is the inverse of stable subordinator, as defined here. Then L is characterized by this guy here. Here we have a Mittag-Leffler function, which is, of course, an analytic function written in this way, you know very well. So this is the first case in which the absolutely continuous functions, this set is not coinciding with the, does not coincide with the W11. Indeed, the Mittag-Leffler function is infinity, absolutely continuous, but not in L1. Okay, but the main important fact, which is also well known, is that as alpha goes to 1, the Mittag-Leffler function becomes an exponential. So we introduce also an exponential random variable and a Mittag-Leffler random variable. So in case alpha goes to 1, since the Mittag-Leffler becomes an exponential, the Mittag-Leffler random variable becomes an exponential random variable. Okay? Okay, so we have to focus on HL, the exponential random variable, the Mittag-Leffler random variable, and this connection here as alpha goes to 1. Okay, maybe this also is well known, but let me recall this equation just to introduce the main object we deal with, which are the time changes you can see here and here. So I have introduced H. Now I am introducing H bar, which is the drifted subordinator. So a subordinator with drift. So we have this process can be considered in order to solve this problem here. Obviously, we have a fractional operator in space. And by means of H bar, we introduce the inverse, which is L bar. L bar obviously is driven by this equation here, can be considered in order to solve this equation, and we have a fractional operator in time. Okay. Main results. So we are looking now at the solution of this problem here in case in which the initial datum is 1. So we are looking at lifetime of the associated process. So the solution is written in this way. In the middle here, you have something written in terms of the first time the process hits the boundary 0. So here, this is the case in which the local time is 0. And this is the case in which the local time is greater than 0. So by putting all together, we can write the solution in this way, only in case in which f is 1. So this seems, this looks very familiar. And the fact is that in the fractional Cauchy problem, the time change is given by the base process B, time changed by L, the inverse. Here we have L bar, let's say time changed if you like, by gamma, which is the local time of X. So something is changing in the representation. Okay, so this is the representation of the solution, and let zeta be the process driven by this problem. So the lifetime of zeta is given by this formula here, where we have the local time less than h bar with an exponential time. Some special cases, the case in which alpha equals 1. So as I said, this condition here leads to the elastic Brownian motion, in the sense that we have the solution written in this way. And as you can see here, this is the multiplicative function associated with the elastic Brownian motion. Indeed, here we have the reflecting Brownian motion. Here we have the local time of the reflecting Brownian motion. And what I denoted by C bar is now C over eta plus sigma, which is the elastic coefficient. So actually, this is the lifetime of a process driven by this generator with this domain. A remark is given here, also in case sigma, which is the drift of a subordinator, here must be negative, which is because we are in the one-dimensional case. This is not possible or quite demanding if we are looking to higher dimension, because in the higher dimension, sigma negative leads to the problem is not well posed. So here is possible because we are dealing with one-dimensional case, and this is the case in which we have negative drift for the subordinator. And for instance, a special case is the case in which we have this equality here, which coincides with the case in which here we have Dirichlet boundary condition. Just multiplying by this guy here, left and right, put this guy 0, you get the Dirichlet boundary condition. This is also standard, this is classic. Okay, this is the case of the elastic Brownian motion, which is quite strange in my opinion, but we are looking just to the lifetime of the process, at least so far. And the intuitive description can be given as follows, in my opinion, that is, we have a neat equation in the bulk. So if you take half derivative, you can move from this representation here to this representation here in the boundary. So by considering these two inequalities here, you get this equality here. And this equality here gives obviously the connection between this fractional condition and this condition here, which is indeed a Robin boundary condition. Okay. The case sigma equal 0. So this is the case in which we have no drift for the subordinator. The problem, once again, takes this form. And the solution can be written in this way, where we have here this guy here, L. So this is not L bar because we have no drift. This is the inverse of H, which is L, time changed with the local time gamma. So the lifetime here, let zeta be the process associated with this problem. The lifetime is written in this way. Here you have the Mittag-Leffler random variable. So the process is killed when the local time is greater or equal than the Mittag-Leffler random variable. As I said, as alpha goes to 1, the Mittag-Leffler random variable becomes the exponential random variable. So we obtain here the lifetime of the elastic Brownian motion, as I said, in case alpha is equal to 1. And the elastic coefficient here obviously is C. Okay, so just to recap a bit, so we have this problem with which is a fractional boundary value problem, or let's say fractional dynamic boundary value problem. So this is the case in which I discussed the one-dimensional case, but this problem may be interesting if we consider higher dimension, of course, as I said before. And the case, so alpha in 0, 1 or 1, 2, and general initial datum F is up to now an open problem. That is the probabilistic representation, because of course I am able to find the analytic solution. And the case in which alpha is in 1, 2 with initial datum F equal to 1, that is the case in which I'm studying the lifetime, which is actually the case, a very simple case in which I am able to find a probabilistic solution. This is an open problem too. And further digression for this problem, this is a joint work with Massimiliano Giona. And in this work, I would like just to give you the idea, by means of which we would like to proceed in order to give a complete characterization of this problem, because there are many problems in the definition and in some other stuff like that. So our idea is that we can proceed by considering two phases. So we have a bounded domain omega, and we have a phase for the bulk and a phase for the surface. So we have to introduce two separate objects, two phases, which are obviously associated or possibly associated with two different processes. Then we have some connection between these two phases to be considered in the problem. And the main fact is that the overall amount of concentration in the closure of omega must be constant. That is, we have a concentration in the bulk and a phase in the surface, and this integral must be constant. This generalizes in some sense previous work given by Goldstein, in which she gave some physical interpretation of the dynamic boundary condition. And so some references. I don't know because if I'm running out of time because oh, okay, perfect. Okay, perfect. Okay, so this what I said so far is collected in this paper here. The paper by Goldstein, in which you can find some references about the physical interpretation of the general, she said, but this is dynamic boundary condition. And the last two references, I would like to spend a few words because this work has been quite inspiring for me because they consider, this is not, to be honest, is not close to the dynamic boundary condition, but is closer to the sticky problem for Brownian motion with drift. And they found some interesting result concerning a boundary condition written in terms of the derivative with respect to time. So I think I can stop here. Many thanks for the attention.
Any questions? Yes.
Very quick question. So you considered this problem so that you have continuous process that represents the solution via the expected value, etc. But of course, you could generalize it using, I don't know, fractional Laplacians or more general semi-group operators.
Yes,
and maybe you are planning to do that. I don't know.
Yeah, of course. To be honest, my feeling is that I have two different feelings on this issue. The first one is that since when we are dealing with fractional operator in space, we are dealing with Markov processes. So in a certain sense, a fractional boundary condition is something which can be more understandable than the case in which you have a fractional boundary condition in time. Because we are dealing here with non-Markov processes in some sense. So I think, but of course, the fractional operator in space requires some technicalities. Then there are two phases of the same problem maybe to be considered.
Okay. Did you think about extension to graphs?
Oh, extension to graph. Oh, okay, so to be honest, our main idea of our group is to consider fractional equation, the macroscopic point of view and the microscopic point of view. So the fact is that the time change can be considered as useful in order to approximate something which is given by a diffusion on irregular domain. So let us consider, for instance, Koch domain is too regular. So you have to consider Sierpinski and something like that. So obviously, graph, this is just very further directions, but very far. But of course, this is the main goal, to represent this kind of problem, that is where you have a geometric characterization of the medium, then to consider an approximation given by this kind of problems.
I have a comment to Enrico Scala's comment. If you are non-local in space, you don't have a boundary value problem anymore, but you have an exterior value problem. That's a totally different type of ball game. Attention.
Yeah. At least we are not considering spectral definition of some fractional operator in space.
Well, if you listen to the first talk, to one of the first talks in the conference by Javier Rosoton, you see the whole problems of that. I mean, already it's a problem to pose the Neumann problem for an exterior value problem. It's not clear what it is.
Yeah, as well. I understand.
Very quickly, I was just curious if you also consider this boundary value problem from a Dirichlet form point of view, and if you can say how to incorporate in the Dirichlet form this fractional boundary condition.
To be honest, we tried to do something in this direction, but the fact is that not so much, to be honest. We tried, but not so much. The fact is that if you are considering the Dirichlet forms, we have to deal with the base process. So it's not clear how to incorporate the fact that we are dealing with time change, so the fractionality in time. And so I don't know.
Okay, let's thank the speaker and all the speakers. Thank you very much.
So the first one is they are in chronological order. That there is